Hello, I am Theresa Stack, an associate professor at Montana Tech, and this learning unit will cover a review of occupational exposure limits, some definitions, as well as help set you up to successfully complete the master's level course in sampling and evaluation of health hazards. The main text for this course, as well as it's referenced pretty heavily in this presentation, is the occupational environment. I use the 3rd edition, but any edition will do. A lot of folks refer to this as the White Book. Another foundational book that's really helpful if you don't do calculations every day is Occupational Safety Calculations, a Professional Reference. This book gives you some examples of how different formulas are used, as well as examples. It's really a neat guidebook. And I have another guidebook that's Quantitative Industrial Hygiene. It's a formula book. This a large portion of this is copied and available for you on Moodle. So again, you can use it to go through different examples when you're doing calculations. So we'll review some basic terms as well as occupational exposure limit calculations, and this way we're all on the same page when we're defining terms and doing different types of calculations. Since there are a significant number of calculations in this class, I just wanted to review significant digits. So in our example here, you can see that 12.3, all 3 of these digits are considered significant. In the next number, 100.2, all 4 of these digits are considered significant. In the next example, .093, only the 9 and the 3 are considered significant digits. And in the last one, 120.30, all 5 of these digits are considered significant. So to review our rules, all non-zero digits are always significant. All non-zero digits are significant, even if there's zeros in between those numbers. If you have a decimal point, the leading zeros are not significant. So in this example, only 2 of these digits are significant. And finally, in the last one, if you have zeros after a decimal point, that last tailing zero is considered significant. So the basic rules are, first, do your calculations. So for example, 1.3 divided by 0.21, and this would give us an answer of 6.1904761. So because we had 2 significant digits for the milligrams and 2 significant digits for the meters cubed, then we really only have an answer where of value are 2 significant digits. So that would be the 6.19, and the 9 allows us to round the 1 up to 2. So our answer would be 6.2 when you're doing your calculations. So first, use your calculator, keep all the digits in place until you get to the end, and then round your answer to the variable with the least amount of significant digits. And hopefully this makes complete sense. I think when we do it a couple of times, we remember that we've been doing this anyways. So a lot of text, but I just want to get everybody on the same page, and so it's really good to start this way in case it's been a while since you've been in Industrial Hygiene 1 or Industrial Hygiene 2. So an OEL, or an exposure limit, is just a generic term used to identify occupational exposure limits. So we use this term in industrial hygiene, environmental studies, safety, health, and toxicology. We sometimes even use this term in the study of ergonomics. A threshold limit value is specifically set by the American Conference of Governmental Industrial Hygienists. And unless a state or federal movement adopts the TLV, it is not regulated by law. But as you know, the TLV tend to be more stringent than the OSHA PELs. and sometimes even more stringent than the NIH RELs, and therefore we use these as guidance. But the TLV is based on group consensus, and it results from recommendations on what the upper exposure limit should be for a hazardous substance, and they base this not only on a collection of toxicological epidemiology data, but also the ability of the method to measure down to that limit. So the next definition is, of course, our permissible exposure limits, and these are set by the Occupational Safety and Health Administration. In 1970, they did adopt the 1968 ACJH-TLVs, and since then, a number of them have been added, and I believe this website will allow us to view, sorry about that, will allow us to view the Z table, which lists the occupational exposure limits, OSHA's, PELs. And so that is where the link can be found. And you can take a look at the different tables. For example, for acetone or acetic acid, you can find the occupational exposure limits there, or the OSHA PLs. We can, of course, also find them in the NIOSH Pocket Guide, which you can either reference from the web, or I have a hard version on my desk. And the last one is the recommended exposure limits. These are set by the National Institute of Occupational Safety and Health, and they recommend to OSHA which limits should be put into place. These are usually later adopted by OSHA when they're able to change the rules or enough information has been found to back them up. So what are the goals of our occupational exposure limits? Well, the threshold limit value of a chemical substance is believed to be a level at which a worker can be exposed day after day for a working lifetime, and I heard that was 40 years, although I did not read that directly from the TLV guide, but Dan and I had a discussion about this. Strictly speaking, TLV is reserved for the American Conference of Industrial Hygienists. Sometimes a TWA, a time-weighted average, can get confused with a TLV. So again, a TLV is an estimate based on known toxicity to humans or animals given the chemical substance and the reliability and accuracy of the latest sampling and analytical methods. So this is really important when we get into developing our sampling protocol, is understanding the analytical methods and the limitations to them to make sure we're measuring the amount of the contaminant in the air that we really wish to. And so we don't want to confuse this with our OSHA PELs. Again, they're found in 29 CFR 1910.1, and it's the Z tables. Some additional terminology used when we're talking about occupational exposure limits is the time-weighted average. This is certainly a fundamental concept, and this is not only used for air contaminants. We can use this for changes in temperature and pressure, as well as changes in humidity, which we definitely measure changes in temperature and pressure when we sample to see whether or not we need to adjust for our sample volume. And we take a time-weighted average of that data, as well as we are trying to collect a time-weighted average of the air contaminant or the thermal exposure. This is usually measured as close as we possibly can get to an 8-hour sample period, because most of the occupational exposure limits, the TLVs and the PELs, are based off of an 8-hour work week. an 8-hour work day. So we want to measure for 8 hours. And this assumes that you're working 40 hours a week. You're not working 48 hours a week. And if you exceed this 8 hours a day or 40 hours a week, then we need to make an adjustment for unusual work shifts. So our time-weighted average also assumes that sometimes you're below a OEL and sometimes you're above an OEL, but over the average of the time, we measure a certain exposure level. An excursion limit is exclusive to the ACGIH and their TLV. So you cannot exceed more than 3 times the TLV for 30 minutes in any given work day. So if you're measuring somebody who is exceeding the TLV, this is allowable to exceed the TLV, but not more than 30 minutes in a given work day. So that's their time-weighted average is above the TLV, and they're allowed this excursion, which is 3 times the threshold limit value for a 30-minute period. If you've measured and you are confident, very confident, that the threshold limit value is not exceeded, then workers are allowed to exceed the TLV not more than 5-fold, but again not more than 30 minutes in a given day. So this is very similar to OSHA's short-term exposure limit. So you're allowed to go over a certain value, go over your OEL for a short period of time, as long as there's a recovery period. So the short-term exposure limit, and STEL, this is a term used by the Occupational Safety and Health Administration, and it's a 15-minute exposure that should not be exceeded during the day. So you have 4 15-minute exposures that are at an STEL, and each one of these 4 15-minute exposures needs to be separated by at least 60 minutes in between. And when we start to talk about sampling, there's some techniques for sampling for an excursion limit as well as a short-term exposure limit. Some of the challenges if you're not using direct reading instruments is, of course, gathering enough air to ensure that you reach the analytical sensitivity of the method. So a ceiling is a concentration that should never be exceeded, and typically we only know that this is exceeded because we're doing some kind of direct reading or continuous monitoring. And an action level is a concentration at which some specific action should be taken. A lot of folks use a blanket term that the action limit is half of the PEL, and certainly many of the OSHA OELs, their action limit is half of the OEL, but this isn't always necessarily true. So we want to be sure we know what the action limit is, and if we need to take action, or sometimes we set our own action limit. We decide to resample because there isn't an action limit that is set, and so we usually use half of the PEL. But the specific definition is that it's a limit. So some other terminology used in our occupational exposure limits, we do see this in the NIH Pocket Guide for Hazardous Chemicals, as well as the ACJH TLV-BEI guidebook, and that is a skin notation. And a skin notation denotes that the possibility of dermal absorption may contribute to the overall body burden. And that means that the inhalation route isn't the only way in which the agent is getting from the outside air into the worker's body and contributing to their biological dose. So this is your skin notation, and therefore the airborne OEL may not be protective. Another term is airborne particulate matter. The ACJH TLV committee generally categorizes this into 3 zones based on where it deposits in the respiratory tract. You have the respiratory fraction, you have the thoracic fraction, and you have the inhalable fraction. And Dr. Hart is going to cover this for the master's level class. She is our resident expert on airborne particle technology and aerosol technology. Some other terms used in occupational exposure limits are the carcinogen classification. A1 being it's a confirmed human carcinogen. A2, it's a suspected human carcinogen. A3, it's a confirmed animal with unknown relevance to human. A4 is it's not classified as a human carcinogen, and A5 is it's not suspected to be a human carcinogen. And I put the classification table down there so you can see how different groups divide out these levels of designations for chemicals in which there may be a carcinogenic effect associated with them. So this is, we're moving on, and this is really an important concept. And so what is the difference between exposure and dose? Really important concept to understand this, because most of the time when we're sampling a worker's exposure. Their exposure is what's on the outside and comes in contact with the organism. Unlike the dose is the amount that actually is internal to the organism, has been absorbed by the body, and has some kind of outcome to it. So your internal dose is the amount of the contaminant that is absorbed by the body, and your biological dose is the amount of the contaminant that is absorbed by the body or is metabolized and interacts with a target organ. And this is not the same as a worker's exposure. The exposure is the amount that the organism is in contact with. We really don't know what gets into the individual and how that is truly metabolized because of individual susceptibility, unless we measure it, of course. Now, noise is the exception to the rule. We use dosimeters, and we assume what is the exposure, what's on the outside of the ear, is also what is reaching the inside of the ear, and that's why we use dosimeters. Also in radiation, of course, you use dosimeters to look at your biological absorbed dose. So we're going to move on to do some calculations. So calculations for occupational exposure limits. And the first calculation that we'll do together is to calculate your concentration. So let's do a calculation to calculate the concentration that we found after we sampled in the workplace. So the formula for a concentration is mass, usually in milligrams, sometimes in micrograms, over a volume of air. We typically use cubic meters, so milligrams per cubic meter. And this is an example of laboratory analysis. You can see that it gave us the milligrams per sample here. And we gave the lab our volume of air. And since we draw that air in liters, we typically report it in liters. So this volume of air is really important because, as you can see, it is the denominator in our equation. And it'll influence our concentration, which ultimately influences our occupational exposure limit assessment, or occupational exposure limit assessment. So sometimes sample volume changes with changes in temperature and pressure, and we need to make adjustments. But we've already reported this to the lab, so we're not going to make any adjustments. We're going to take our sample volume in liters, and I'm going to convert it to cubic meters. So I have the right units when I go and do my concentration calculation. So my concentration is milligrams per cubic meter, which is 0.37. I got that from there, over 1.2187. Put that in the calculator. 0.37 divided by 1.2187. It equals 0.37 And we only have 2 significant digits here, so we can only use 2 significant digits, which means our answer is having this 0 here lets you know that this is a significant digit. It's a significant 0 in this after the decimal point, so we keep it there. And that's how we calculate our concentration. Now, if we needed to convert our concentration, which means we had milligrams per cubic meter, or we had parts per million, and we need to convert back and forth, then we can use this equation to do that. We just plug our numbers in. It's pretty straightforward, although it does assume that we're using normal temperature and pressure to be able to use this constant. So if our lab reported 25 parts per million toluene, and we want to know how many milligrams per cubic meter we have, we just need to know the molecular weight of toluene. And you can find that in the NIH Pocket Guide. You can find it on the analytical method itself. And now we just need to isolate our variable and solve. Some people do this different ways. I'll show you how I do it. And we only had 2 significant digits, so our answer is actually 94 milligrams per cubic meter, which is 25 parts per million toluene. Then we're able to do our conversion back and forth from parts per million to milligrams per cubic meter. So let's just do a calculation so we can calculate our sample volume. So we use this formula, Q, which is our flow rate, equals volume over time. So our Q is in liters per minute. And if we need to solve for our sample volume, how much air did we draw through the system over a period of time, we could just use this pretty easy formula. So if we sampled at a rate of 2.5 liters per minute for 480 minutes, what is our sample volume? We pulled 1,200 liters at 2.5 liters per minute for 480 minutes. This assumes we're not adjusting our sample volume for changes in temperature and pressure. So for our next calculation, we'll calculate a time-weighted average. So if we only drew one sample, then our concentration would be our time-weighted average because we're weighting it over that one duration of time that we used. But when we take multiple samples, which is integrated sampling, which is completely preferred, because that way, if possible, given the method, we're able to better track when people's exposures occurred, kind of those low periods and those high periods. And so this is a graphical representation. You can see that if here is your permissible exposure limit, and this is your action limit, that people were to the permissible exposure limit and then up above the action limit and down below, and then they almost reached a ceiling at some point, and then they fell back down below. And so we're trying to average what their exposure was over a period of time. That's your time-weighted average. And the formula is the sum of concentration times time divided by the sum of time. And so we'll do an example together so we could calculate a time-weighted average. So we're moving to that point of evaluating the exposure. And here we're completely assuming that all our sample rates were appropriately recorded and adjusted for changes in temperature and pressure. Okay, so let's calculate a time-weighted average. So our first step is we need to know what our sample volume was in liters. So we took two samples, one of them for 240 minutes, the other one for 210 minutes. These are both off of the same workers. So we sampled for a few hours and we sampled for a few hours more. Our average sample rate, our Q, would be the same because we would take our pre and our post and we'd use it for both because we wouldn't be changing our pump out very much. So let's calculate our sample volume. So we'll go back to the formula. So we got 2.204 for our sample volume. And I'm doing the first one. And now I'm going to go from liters to cubic meters. Oops, wouldn't have done that right. All right, for our first one. And now we'll do the second one, where we just have a different time. So we have our sample volume in liters, we have our sample volume in cubic meters, and now we need to calculate our concentration. So we have our mass back from our lab. And we have the mass back from the lab on the other sample. And now we can calculate our concentration. Right, so now we have our concentration in milligrams per meters cubed, and we just need to time weight them. So we're going to do that next. So to time weight them, it is the sum of concentration times time over the sum of time. So we have 5.68095 times per time plus our next concentration. Times our time. Over our sum of time. And if we do this appropriately, we should come up with the right time-weighted average. Let's give it a try. So we now calculated our time-weighted average. So the values are entered into the table, and you can see that they give you the same results as we had gotten when we done them longhand on the paper, but I wanted to show you the math so that you can work through it in case you're a little rusty in calculating your time-weighted average. And so in summary, our occupational exposure limits, they're generic terms. We're really evaluating our exposure, which is what is in contact with the organism on the outside, against an OSHA permissible exposure limit or an ACJH threshold limit value. We typically do this by calculating a concentration or a time-weighted average. Sometimes we have to convert back and forth from parts per million to milligrams per meters cubed or cubic meters. And also remember the difference between exposure and dose. Dose is what is internal to the organism. It's the concentration that's absorbed by the body over a period of time versus the exposure, and the exposure is with which the worker is exposed to or in contact with. So this summarizes our industrial hygiene review. Please go through that information sheet with some different calculations, and I'll go through them as we continue on with the course. Have a great day.